Okay, are you ready, Linsu?
Yes.
Okay, thanks for staying late for us. It's 9:30 though, I guess.
Yes. Yes. Not too bad. Yeah.
Okay, so we are very happy to have today Linsu from Tsinghua University, and we will speak about interface for quasisplit GST, GSO, over geometry.
Okay. Yeah. Thank you for the introduction. I'm very happy to give talk in this seminar. So I'll be talking about the A packets. So let me start with some global motivations. I'll take K to be a number field and G to be a symplectic groups. There's a similar story for even orthogonal groups, but just the notation will be slightly more complicated. So I'll stick with symplectic groups. But in one place, I'll talk about even orthogonal groups. So let me start with the theorem of Arthur. So I think a fundamental problem in the theory of automorphic form is to determine the discrete spectrum. And Arthur made a conjecture for general connected reductive groups. And he also proved this conjecture for symplectic and orthogonal groups. So in the case of symplectic groups, the discrete spectrum will decompose according to these A parameters, psi. And for each A parameters, you will have a packet of irreducible admissible representation of the p-adic group. And then for this representation in this packet, we associate a multiplicity. And in case the multiplicity is 0, that means this representation is not automorphic. Okay, so let me say, if you explain, here you have these parameters, packets, and the multiplicities. So let me begin with these parameters. So conjecturally, these are morphisms from a hypothetical group, LK. So this is conjectured to be an extension of the global weight group, and you map it to the dual group. So here G is a split, so I'll just take G check, and it is equal to SO word. Okay. And since this group LK is not known yet, so to make this theorem like precise, we have to embed this orthogonal group to general linear groups. So that will be GO2M plus 1C. And well, suppose we still take this hypothetical group LK, and now you can view this parameter instead as a representation. So then it's natural to decompose it into irreducible subrepresentations. And moreover, for each irreducible subrepresentations, you would expect that it also can be written as a tensor product of the representation of this hypothetical group LK, and then irreducible representation of this SL2C, which should be a symmetric power. So let's say the dimension is Bi. Okay. And now this mu I is supposed to be an irreducible representation of this hypothetical group LK, and conjecturally they corresponding to automorphic representations of general linear groups, cuspidal automorphic representations. And also it will be, sorry, we would require that it is self-dual. So this mu I can be interpreted as a self-dual cuspidal automorphic representation. Of some general linear groups. Okay, and in this way, you can actually interpret the A parameters just as pairs of these mu I and bi. Okay, so these are completely determined parameter. And then we come to the packet. So the packet should be decomposed as a restrict tensor product, just like an individual irreducible representation of the adic group. And here, so the local packet is going to be a finite subset of irreducible representation of the local group. So it's either real or p-adic. And to categorize this, we still go to the general linear group side. So it is associated with a representation of GO2m plus 1. And so this is an irreducible representation. And the relation is given by the so-called twisted endoscopy theory. So there's a causal relation between this GON general linear group, this representation of GO2m plus 1. And there's also a stable distribution that you can get from this packet for the local group. Okay. And finally, to get the multiplicity, we also need a map from this local packet to the set of representation of a finite group. And this finite group is the component group of the centralizer of the parameter modulo the center of the dual group. Okay. And in fact, in this case, what you get is a two group. So it's a billion. So for simplicity, I'll just call it the centralizer group for the parameter. Okay. So for each representation in the packet, you will get a representation of this finite group. We also view this as a character for this finite group. And then globally, you can also consider the centralizer group. And it mapped to the product of all the local ones. And by this homomorphism, we can take the tensor product of all this this representation for the local centralizer group. We can define this epsilon pi, which should be the tensor product. And in fact, this makes sense because when this pi v is unramified, then the associated representation epsilon pi v will be trivial. Okay, so here you only actually get finite many non-trivial representations. In the end, we can use this epsilon pi to define the multiplicity. So that's Arthur's multiplicity formula. And it basically says that you can take the inner product of this, this character epsilon pi with another one coming from the parameter. So it's defined by this parameter. So to write down the inner product. Okay, so it's like this. And so that's the multiplicity formula. Okay. So our goal is to extend this theorem to the general symplectic groups and also general even orthogonal group. That will have application in the study of Schummer variety. So let's look at the general symplectic groups. So by definition, this is the group of linear isomorphisms preserving the symplectic form up to a scalar. So in particular, it will contain the symplectic groups. And also you will have a character from G tilde to the multiplicity groups. So that's the similitude character. So we have an exact sequence. So for example, if you take SP2, that's just SL2. and the GSP2 is GL2. Then the similitude character is the determinant map. Okay. And on the dual side, so you have the dual group of general symplectic group, and that is the general spin group. Okay. And you can actually have a very concrete description of this group using the Clifford algebra. Okay. So it has a concrete description. And also there's this spinor norm. So it's like a determinant map. The kernel is the spin group. And if you restrict the spinor norm to the center of the general spin group, this map is just given by square. Okay. Okay, that's the dual side. So now we can formulate a conjecture, and this is still due to Arthur because he made a conjecture for a general connected reductive group. So here we need to fix central character for the general symplectic group. And then the conjecture says the discrete spectrum will decompose according to the A parameter, and also you can get a packet, and then you have the multiplicity. Okay, still the three things. Okay, and again, we're going to explain these three things. So starting from the parameter, so you see here, we have to make it compatible with the central character. So how you can read the central character from the parameter? What you do is you can compose the parameter with the spinor norm. And in this way, you actually will get a character of the global wave group. So by class field theory, you know that it will give you an ideal class character, and that corresponding to the central character. In the case of symplectic groups, or also even orthogonal group case, what Arthur did is to take the standard representation of the dual group. So if you want to do something similar, the natural thing to do is to take a representation of the general spin group. But then there's no good endoscopy theory to describing that lifting. In particular, we don't have a trace formula. So it's very hard to work with that. So instead, to parameterize the A parameter for G tilde, what we do is we take the projection of the dual group from the general symplectic groups to the symplectic group, to the dual group of symplectic groups. And in this way, you will get a parameter for G. And if you fix the parameter for G and look for all the possible psi tilde, okay, then you see they are all differ by a twist of a character. So the twisting is on the center of these general spin groups. And since here we are fixing the central character, and also you see that the spinor norm, when you restrict to the center, it's just a square. So because of that, all this psi tilde, once you fix psi, they are all differ by a quadratic character. So I'll just denote the set of quadratic characters by Y, both on the Galois side and also on the automorphic side. Okay. Okay. So in this way, to parameterize the A parameter for G tilde with this fixed central character, it should be in bijection with pairs y psi is a parameter for G. And also you have to take a quadratic character. So this omega in Y. It is possible that this quadratic character can stabilize, say, this parameter psi tilde. So you have to module out some finite groups, which I denote by alpha S psi. So where does this group come from? So here, let's say we have this parameter psi and psi tilde as they are conjectured to be. So we take the centralizer of psi tilde. It actually included into the centralizer of psi just by the projection on the dual group side. So this is an inclusion. And then the difference is measured by a morphism alpha to y. Okay? And the way you define this is you take any element in S psi, so that should come from something from G check, which stabilize psi. And you just find its preimage, any preimage in G tilde check. And that element should stabilize psi tilde up to some element in the center. And that's how you get this alpha, okay? Now you may think, well, like in general, what we don't know what this psi tilde is. In particular, we cannot define this psi tilde since it involves this hypothetical group LK. The point is, say in Arthur's theory, he replaced this psi by certain data coming from the automorphic representation of general linear groups. And moreover, he can give a definition for this S psi, even though we don't have it in the conjectural form. And moreover, you can actually define this alpha just from Arthur's definition of this S psi. And then you can define S psi tilde just as the kernel of alpha. So here's the example. It's actually very easy. So if psi can be written as mu1 tensor, this sim b1 minus 1, and then direct sum with mu2 tensor sim e2 minus 1. So you have two components. So you can think that, so the parameterizing data is just mu1 b1 and mu2 b2. So in this case, this S psi is going to be z mod 2z, okay? So you can see the pattern. So it's somehow related to how many irreducible components you can get from here. Now to define alpha, we can take a non-trivial element. Okay. So this alpha S should be given by some quadratic character at I to the power bi. So here this at I is nothing but the central character. Of this mu I, okay? So recall that this mu I is some self-dual automorphic representation of some general linear groups. And because it is self-dual, the central character is going to be quadratic, okay? And it raised the power to bi. And in fact, in this case, so this eta 1 b1 is actually equal to eta 2 b2. So they give you the same thing. Okay, so you can define it in this way. So then you can define this as psi tilde just to be the kernel of this alpha. So for example, if this at I bi is non-trivial, then you have trivial centralizer group for psi tilde. Okay. So that's for the parameter. And then we move on to the packet. Again, we conjecture that the packet should decompose as the restricted tensor product. And moreover, here, if we twist the global parameter by some quadratic characters, then you should also have a twist on the corresponding packet. So that's something very natural. And then when you move to the local packet, here we don't have a categorization using a representation of general linear groups. So instead, what we do is we restrict to G, and we require this gives you back the packet for G. Again, that's also a natural requirement. And then to define a multiplicity, we need to have a map from this packet to the set of representation of the centralizer group. And in fact, we can define such a map, not just for this packet, but for all the representations of G tilde with a fixed central character such that the restriction to G give you a representation in the packet for G. So this is included in high V, and so the central character is equal to theta tilde. Okay. So from this set, we would like to define a map to the set of representations of S psi tilde V. And the idea is very simple. So if you take any irreducible representation on the left-hand side, you can restrict to G, and well, that might decompose into several irreducible representation. Okay, and you find their corresponding representation on the centralizer group. They may be different, but once you restrict to this S psi tilde, they will be the same. And this is actually a consequence of the endoscopic character relation for this A packet of G. Okay? You just study the endoscopic relation under the conjugation by G tilde, the general symplectic groups, and you will see that. So you have a well-defined map on the top, and the packet should contain inside. Okay? So you also have a well-defined map from this packet if you know what that is. And finally, for the multiplicity formula, it's the same kind of a formula. So you have this character from pi tilde, and also you have a character from psi tilde. And for this character, it can be defined as the restriction of this epsilon psi. Okay. And in fact, this is also compatible with Arthur's conjectural formula for this character epsilon psi. Okay. So we have explained all these things in the case of general symplectic groups, and we can put them together and formulate another conjecture, which we hope eventually can be proved in the future. So our goal is to show for any parameter of G is the symplectic groups, there exists a packet for G tilde, and it is well defined up to twist by some quadratic characters. And with this packet, we can decompose the discrete spectrum for this G tilde. So the first two sum corresponding to the parameters for G tilde. So since we don't have them, we have to replace that by the parameters for G and also quadratic characters. And then the packet is in the conjecture, and the multiplicity formula is given in the previous page. Okay. And as you can see, in order to prove this conjecture, the crucial thing is to have this global packet. And what I'm going to present is the construction on its local component. Okay. So any questions so far? Okay. So now let me talk about the main results. So I'll take F to be a p-adic field. I'm still take G to be symplectic. There's a similar story for even orthogonal groups. In the local case, we can specify the A parameters. So it is a homomorphism from the weak dealing group cross SO2C to G check. There are two distinguished cases The first case is when this parameter is tempered, namely it is trivial on SL2C. Okay? And my early results show that you can actually find a packet for such tempered parameters, which is well defined up to a twist by local quadratic characters. It satisfies two properties. So first, it gives a disjoint decomposition for all the representations whose restriction is in the packet for G, and with this fixed central character. But this is something very easy. The first condition is very easy to satisfy because what you do is you just choose some representative among all the possible extension of a representation from G to G tilde with this fixed central character. Okay? To just choose some representatives. The crucial statement is the second one, which is if you sum over the representation in the packet, which means you're choosing specific representatives in the first step, then you want this virtual representation to be stable, okay? And these two conditions will categorize this packet uniquely up to a twist. Moreover, we can show this packet satisfy the character relation. What this means is if you have a parameter which facts through certain endoscopic group, which I denote by H tilde. So the dual group is H tilde check. Okay. Well, you can still project to G check. Okay. And that will also facts through some endoscopic group for G, which we denote by H. Okay. So for this H check, so by the definition of endoscopic groups, it should be the centralizer of some semi-simple element, and you take the identity component. So this S certainly should be contained in the centralizer of the parameter for G, okay, after the projection. So the statement is, once if the parameter phi tilde affects to some endoscopic group for G tilde, you can also define an L packet for H tilde. And you can also have a stable distribution. And if you take the endoscopic transfer, that should be equal to an invariant distribution on G tilde. So which is the expected form. So it's a linear combination of representations in this packet, okay? With the coefficient is given by this character. And so what is this packet on the endoscopic groups? So here I'll give example. So let's say G is symplectic. Let's take the endoscopic group to be an elliptic endoscopic group. So it will be in the form SP2M1 and SO2N2, okay? And now if we take G tilde, its endoscopic group will be written as G SP2N1 cross SO2N2. So what is this group? You can actually embed this group to GSP2N1, the general symplectic groups, and also GSO2N2, the general even orthogonal groups. And from these two groups, you will get two similitude characters. So this H tilde will just be the group of elements where these two similitude character matches. So they are equal, okay? And that characterizes this group H tilde. So to define a packet on edge tilter, what you can do is you first get the packet for GSP and also GSO. You take the tensor product and you restrict to edge tilter. And that's how you get the local packet on edge tilter. And also you will get a stable distribution there. And then the endoscopic character relation is just as yeah, it's just this one. So that's the character relation. So this is a temporal case. And now let's move on to the non-temporal case. Ideally, you would expect similar results, but there's some difference. So first, what we have is the existence of some packet. We don't have the uniqueness. Secondly, we don't get a disjoint decomposition. So here we only say that the restriction gives you back the packet for G. But we also want some stable distributions. So here, if you do the representation with this coefficient, and that's also in the conjecture, is compatible with the conjecture. So this S psi tilde is the image of the non-trivial central element of SO2C. Okay. So this is compatible with the conjecture, and the statement is that this is stable. Okay. And secondly, this packet will satisfy some character relations as in the temporal case. So here's some remarks. First, we not only show the existence, we actually construct this packet explicitly. So it's given by construction. And secondly, you would not expect the disjoint decomposition in part A, as in the temporal case. So what you see in the non-temporal case is if you twist by characters, okay, they may not be disjoint. Okay, but nevertheless, what you can do is you can still take the representation in the packet for G, the symplectic groups, and try to extend or lift them to the general symplectic groups. And you just choose representatives. You can still do that. Okay. Finally, if you still want some kind of uniqueness result, so this is what we have. So if we take some parameters, so this is again a parameter for G. And if this satisfies some combinatorial conditions, maybe I'll mention that in the very end, then the packet shows up in the previous theorem is uniquely characterized by the two properties A and B. Okay? And it's unique up to some twist. Moreover, you can actually get all the A packets in all cases from the ones satisfying these combinatorial conditions, but maybe for bigger groups. And the way you get them is by taking the Jacobi module. So in this sense, you do have a kind of unique way to categorize the A packets for general symplectic groups. So you just have to first categorize them in certain cases, and then you apply the procedure of taking Jacobi modules to get all the others. Okay, so these two are the main results. So before talking about the construction, are there any questions? Okay, so let me move on to the construction. Okay. And I'm going to present two constructions. I think the first one is more kind of, it's more kind of neat. The second one is more kind of in detail and more complicated. So the first one is to look at this question from a general picture. So I'm going to take G to be a general connected reductive groups, okay? And how we are going to think about the A packets for general G. So first, a simple fact is if you look at the set of A parameters, it includes into the set of length parameters, the L parameters, and it's given by this map. Okay, and once you have this, there are two natural conditions for this A packet. First, it should contain the L packet associated with this L parameter. Secondly, you want the elements in this A packet to have the same infinitesimal character. So we know what the infinitesimal character for representation of real groups. That's given by the center of the universal empty-looking algebra. But what's the meaning for representation of p-adic groups? So this is the idea of Moeglin, that you can get the infinitesimal character through the local length correspondence. So if you have a local length correspondence, then you can try to define the infinitesimal character for a length parameter. And it is going to be a homomorphism from just a way group to the dual group. And the way you get this is very similar to how you attach L parameter to A parameter. So you just try to Q one SL2C, okay? So if you define in this way, you can fix the infinitesimal character in the beginning and collect all the representations with this infinitesimal character. You can also consider all the length parameter with this fixed infinitesimal character, so which I use subscript lambda. And this set has a nice geometric description. They corresponding to orbits in an affine space, V lambda. So this V lambda is the Q eigenspace of the adjoint action by the Frobenius on the set of fixed points on the Lie algebra of the dual group under the adjoint action of the inertial subgroup from the wave group. So this Q is the number of elements in the residue field of the local field. So that's V lambda. So it's basically an affine space in the Lie algebra of the dual group. And this H lambda is nothing but the centralizer of the infinitesimal character lambda. Okay. So they all corresponding to orbits in this affine space. And then we can make a conjecture, and this is due to Adam Babbage Morgan, and well, that's in the real case, but also Morgan extended to the p-adic case. So the conjecture says that, well, this A packet should consist of representations with the prescribed infinitesimal character, and also these representations, their L parameter, and you look at the associated orbit, they will satisfy this closure relation. Okay? And in fact, so Adam Babbage Morgan and also Morgan, they made more precise conjecture. They can put equalities here by imposing some geometric conditions on the right-hand side using perverse sheaves and the characteristic cycle. But since our problem is really to extend the A packet from G to G tilde, so we don't actually need that extra geometric information. So I'm not going to talk about that. And here's a remark. So we need to assume local lengths to make sense of this conjecture. And for G is symplectic groups, but also true for orthogonal groups. We have the local lengths. This is by Arthur. We also know the A packet for these groups do contained in the set of representations with the desired infinitesimal character. And that is by the workers Moeglin on the structure of these A packets. So we do know these things. But what we don't know, and it seems to be very subtle, is about this closure relation. Okay. You may think this is some kind of combinatorial problems, but it's just too, I feel it's too complicated. So I think this is not known. And I think this is related to the kind of so-called p-adic analog of Castaner-Lustig conjectures. It's about some kind of induction multiplicities. Okay. So if you have like Castaner-Lustig, then probably you can conclude such kind of thing. Okay. So now we can also look at the picture for the general symplectic groups and compare these two pictures. So we take an infinitesimal character for G tilde. You can take the projection and get an infinitesimal character for G. You can compare the set of Lagrange parameters with these two infinitesimal characters. And first you observe that this space V lambda tilde is actually isomorphic to V lambda because they are basically nilpotent elements in the Lie algebra of the dual groups. Okay? But the group acting on these two spaces are different. For V lambda tilde, the action by H lambda tilde affects through this quotient, quotient by the center. And this is a connected group. And in fact, it's the identity component of H lambda. So from this, you can see that you have a surjection from the parameter for the Lagrange parameters from G tilde to G, but in general, it's not injective. You can interpret this as saying that choosing a lift for the infinitesimal character cannot distinguish a lift of L parameters in general, okay, if this is not injective. And if you do want to distinguish an L parameter, what you do is you have to impose some closure relations. And that's exactly what this conjecture says. So if you already have the A packet for G, then you can formulate the A packet for G tilde just to be the set of representations with the desired infinitesimal character. And also you want the restriction to be contained in the A packet for G. And also you put this closure relation, which kind of distinguish a lift for L parameters. And as I said that we don't know this for the case of symplectic groups. And in general, it's kind of subtle. We also don't have the Castaner-Lustig. So I just want to point out, so in a nice case, when this delta is a bijection, then we can just drop this. We can drop this closure relation. In other words, in this case, all we need to do, or all we need to know, is how to determine the infinitesimal character. And as I said, you need to have local Lagrange. Okay. So you need to have some local Lagrange or some version of local Lagrange to get the infinitesimal character. So the idea is just to choose one. So just record that in the temporal case, we have this L packet, which is only well-defined up to twists. So you can associate a parameter E tilde with the packet, but this is not going to be unique. But you can fix a choice by imposing a condition. Okay. So the following conjecture, LLC plus, roughly speaking, says that you want the parabolic induction to preserve the infinitesimal character. So it sounds very natural to expect. So this statement is due to Thomas Hames. And he put this condition into the usual local Lagrange correspondence and called that LLC plus. So what I've stated is really the plus part. Okay? And in the case when G is symplectic, and also true for orthogonal, this is known, and this is due to I would say this is known by the work of Musavi. Okay. So now what we want to do is we want to fix a choice for the local Lagrange correspondence so that this condition holds. So that's the first statement in the theorem. And once you have this, then you can tell what the infinitesimal character is. And if this delta is bijective, which means that you don't have to worry about the closure relation, then you can define the packet. And when you form this linear combination, that will be stable. And in fact, the stability follows from this LLC plus. So you do need that. Okay. So in the end, let me talk about the general case, which is you don't have this bijection for this delta. Okay. And in general case, we go back to a construction of Moeglin for the classical groups. And this case also recover the previous one. So actually you can just go to the general case and construct all the E packets at one time. And for this one, we have to be more specific. So I'm writing down this A parameter. I'm also writing down the weight delane group as the weight group cross SL2C. Okay? And we take an embedding of the dual group to the general linear groups. So you can view this psi as a representation and naturally decompose into irreducible component. So here I made some assumptions to simplify it. So I'm going to fix rho for the representation of the weight group. And then this rho by the local Lagrange correspondence for general linear groups will correspond to certain, excuse me, self-dual irreducible unitary supercuspidal representation of general linear group. And I'll also denote that supercuspidal representation by rho for simplicity. And let me also assume that this is of orthogonal type. Okay. Then I'm going to assume that AI plus BI is even. This is just some parity reasons. And finally, there's a combinatorial conditions. To formulate that, we need to transfer AI BI to capital AI BI by this kind of strange transformation rule. And the combinatorial condition is you want these intervals obtained from AI BI are disjoint. Okay. And in fact, this case is called the case of discrete diagonal restriction by Moeglin. What this means is if you look at the associative packet for G, the only temporal representation, well, the temporal representation in this packet are all discrete series. Okay. And a remark. So once you have these combinatorial conditions, you can also compare this with the temporal case. So you will see that the capital AI is equal to capital BI, and this is equivalent to small bi equal to 1. And that means exactly, so for this irreducible component, the second SL2 is trivial. So from this, you can see this psi is tempered, corresponding to the fact that if you sum of all the lengths of intervals, you will get 0. Okay. So next, Moeglin was Boucher, they gave a very nice recursive formula, which basically reducing this sum of lengths of these intervals. So in the sense that you kind of reduce to the temporal case. So here's their formula. It's a very complicated formula. So first, we're going to take this linear combination of representation in the packet. And we know that this is stable. So this is a stable distribution coming from the A packet. You view that as a virtual representation. And this is a theorem of Moeglin-Boucher. So the idea is try to reduce the length of intervals. So you fix one interval with a positive length. And then you express this virtual representation by using two virtual representation associated with two different A packets. And the formula can be viewed in two parts. The first part is an alternating sum, and you take a virtual representation and you're going to take a Jacobi module, okay? And usually when you take a Jacobi module, you reduce the Levy subgroups and there will be some general linear factors. And here you just put some conditions on the representation of the general linear factors. And then you just throw the general linear factor away and just keep the classical group part. And then you take a Steinberg representation with some twist, and then you do a parabolic induction. So that's the first part. Anyway, you don't have to kind of capture all these things. The important thing is that you have this another virtual representation from a different egg packet. The second one is just this virtual representation from another A packet with some sign. Okay. And so from Kasai 1, Kasai 2, so they are obtained by replacing AB with some other intervals, though they corresponding to other irreducible components in the parameter. And as you can see that the length of the intervals do get reduced, okay, in this way. So if you apply this formula, you can eventually reduce to the temporal case, okay? And that's actually also the idea of Moeglin to construct these packets, okay? Because if you don't have Arthur's theory, so a priori, you don't have a definition for these virtual representations. So what you can do is you can just construct them by using, say, the right-hand side of this formula. So it's complicated, but you can do. And so you can really start with the temporal case and then work out all the A packets, or the A packet in this situation. Okay. So for us, the idea is clear. We have the tempered packet already. So we can just plug in this formula and try to generate the A packets for G tilde. The issue is because we need to take some kind of lift. So these, so this say tempered packets, they only well defined up to twist. And in this formula, you have two virtual representation from two different packets. And also these things are only well defined up to some twist, as you can see from the tempered case. So the natural question is to make some compatible choices for these things. And in fact, the idea is you're going to construct these A packet in a family. Okay, so they are all compatible in a certain way, and this is by induction on the length of the intervals. Okay, so eventually you reduce to a temporal case. So the definition or the construction for the packet is just to use the previous formula. You have two parts. The only extra stuff is this twist. Okay. So you're going to twist the character for this virtual representation from psi 1 tilde. Okay, it looks like a complicated character, so it has three parts. This eta rho is the central character of rho. So remember, rho is a superclassical representation of general linear groups. And this omega rho is just the absolute value to some power. And finally, this chi rho tilde. So you should view this this packet, so parameterized by rho tilde, as in the family. So we construct a family, and this is actually in the family. So we actually choose one specific packet. This is a tempered packet, and it's a singleton. So they only contain one single, actually supercaspital representations of some general symplectic groups. And you choose the central character of that representation. So it's a central character for the general symplectic groups. Then you put them together in this form. So how you think of this twist theoretically? So you can actually divide this twist into two pieces. So this part is actually very easy to predict, okay? So I didn't tell you where they come from. So this one is very easy to predict. It comes from the requirement of compatibility of infinitesimal character, which means that in this formula, you have these two parts, and you have to make this twist so that all the pieces, all the representation shows up in this formula will have the same infinitesimal character. So that's a natural condition. The second twist is more subtle, and it is responsible to afford the closure relation that I talked about in the early construction, or it should be, because we don't know yet. One evidence is if this eta row is actually trivial, then you are in the situation where the delta is bijection, which means that the lift of infinitesimal character do specify a lift for the L parameters. Okay, so you don't have this issue. So this eta row, when eta row is trivial, you actually can get to the packet from the previous construction. So this is related to the closure relation. And finally, the result is if you take this formula, because there's a lot of plus minus, so you will expect a lot of cancellation. If you look at the formula for the case of symplectic groups, after you do all the cancellations, what you left is just the representation in the packet. So now you hope that when you take the formula to G tilde, you can still have those cancellation. So in the end, what left in the left-hand side is just the representation which kind of extended from the packet of G. So that's the main difficulty, which is to show that any cancellation happening on the side of, on the level of G, also happening when you lift it to G tilde. And in fact, that's how I get this twist. So this twist is really coming from the calculation, so that you do have these cancellations. But then later you track that, well, this second part is matched the infinitesimal character. The first part is what we expect to relate to the closure relation, but we don't know. That's just come out from the calculation. So the final result is that you still have those cancellation, and in the end, what you get is just those representations kind of lift or extended from the packet in G. There are no other things. And that also gives you the definition for the packet for G tilde, because you can just take all these representations in this virtual representation at the psi tilde. So that's how you get them. And finally, for the stability, that actually follows immediately from the definition, because in the definition, you're starting from some virtual representation, which can be assumed stable. And then in this formula, what you see is just by taking Jacobi restriction and the parabolic induction, and all these procedures will preserve a stability. So just from this formula, you know it is stable. Okay. Okay, so this is a kind of special case, but I think this is the critical case. And so it is easy to get the A packet from the, in general, from this case. Okay, so I think I'll just stop here. Thank you.
Thank you very much. Questions, please?
Yes, can I ask a question?
Yes.
Of course.
This A packets that you get, the local ones.
Yes.
Who are the experts in that? Who are the, I mean, I don't know if there are too much research on the structure of these A packets, except yourself and maybe Moeglin Wolfsberger.
So the question is, what are the works involved in these A packets?
Yes.
For the local structure, I really don't know. I mainly follow the works of Moeglin. She did plenty of works maybe like decades ago. And also more recently, she's working on the Archimedean case with David Renat. I think maybe the early motivation for her is to prove the multiplicity-free results for these A packets so that you can get some kind of a multiplicity 1 result for a non-tempered spectrum. And another reason for studying this is to describe the residual spectrum. So Moeglin and WIS persuaded describe the residual spectrum for the general linear groups. And so it's a natural question to describe the ones for the symplectic groups. And but that's not your question.
How much of the A packet is outside this Langland's L parameter? I mean, in the case of, I mean, I remember from Arthur's even earliest work for PSP4, yes, there was some holomorphic forms. They were always holomorphic. They weren't generic or anything, which were complementing this non-tempered ones. So in your packets, I mean, how much outside that Langland's L packet are, what are the elements?
Oh, what are the actual represent, yes, okay. You can actually have a very precise description for them. For example, in general, say if the other parameter is not a temporal one, then the associated L packet consists of all non-temporal representations. But when you enlarge that to A packet, you actually could include some temporal representations and even supercuspidal representations. And
I mean, in the case of PSP4R, I think the examples that Arthur has, they are all holomorphic discrete series. And I think you will never have a generic one showing up for Ziegler forms or things like that.
Yes, you don't. I think the general belief is that you don't have. So if the other parameter is not tempered, then you don't expect a generic representation in the A packet.
Yeah.
So I think that's a general belief.
Okay, that's a general. Okay.
Yeah, I think. Yeah. So
I'm not too wrong on that.
Yes. I think they're actually a very nice. So Adam Babbage Wergen and also Wergen, they have a geometric conjectures about these A packets. We still don't know yet. It's a local conjecture, but it's very precise. So once you know the local Langland correspondence, you can use the preferred sheaves on the space of Langland parameters. And from that perspective, it's actually very easy to see why the generic representation cannot show up in the non-tempered A packet. So it can only show up in the tempered case. And it's very easy because the general representation will corresponding to the constant local system on the V lambda, what I described. It's an affine space. And I think this is only a few cases that we can tell the characteristic cycle without even doing any computation. So in general, the geometric description is very hard to compute. You have to compute some characteristic cycle for preferred sheaves. But for the generic representation, it's a constant local system.
Yeah, it agrees with my thoughts. I think I agree with it. Yeah. That they shouldn't show up in the non-tempered packets. Yeah. Okay, thank you. Very nice talk. Thank you.
Thank you.
More questions, please. Are there any more questions? If not, then thank you again.
Thank you.
Next week, we have no seminar due to the Sukkot holiday in Israel. And in 2 weeks, we have Spencer Leslie. I'll see you in 2 weeks.
See you.
Chag Sameach, everybody.
Chag Sameach.